This is the third part of our optimization series. In this one here, we're going to have a look primarily at how we store values in memory, but we'll also touch upon temporary variables as a way of linking in to the next talk. We'll start off looking at the stack or the heap. So in C++, we as programmers get to choose where it is we want our data, our instances of class or primitive data to be created, to be stored. We can allocate them on the stack or indeed allocate them on the heap. Now, we have sort of looked at this here, that if we are allocating a variable or an instance of a class on the stack, it is actually quite quick to do. We simply reserve a chunk of memory, we pass our update or pointer, and that's that. And to free it up, we're just reallocating the pointer back again. Whereas if we allocate something on the heap using the new keyword, then we've got to go and find and reserve a chunk of memory. And then when we delete it, we have to remember to delete it from it too. We then got to go back and to free up that and potentially rearrange memory. So generally, if possible, and if nothing else is a factor determining this, it's better to prefer creating our objects and our data on the stack as opposed to on the heap. Now, if something is long-lived, it's to be shared across multiple methods and things like that, then it's going to have to be created on the heap. But if other things, if it doesn't have to be that, if it's just something that the method's using and then we'll discard at the end, do create it on the stack as opposed to allocating it on the heap. It'll work out then to be faster. The actual notion of how we create it also applies to internal data within objects. So we have two examples of foo shown over on the right. In the top one, so class foo, line 7 and line 8, you can see the private data. So it is a private element of data, some class, and we're actually having a pointer to that instance. And when we construct foo in line 4, we're creating a new instance of the thing we're pointing to on the heap and then linking to it. And our destructor is that we've got to then remember to delete it off the heap whenever foo gets to be deleted itself. So in this case, we create an instance of foo. Now, the instance of foo that we create, it could be in the stack, it could be in the heap, doesn't really matter. But foo itself, when it is created, allocates one of its own internal items of data on the heap, which it then has to free up whenever it's been deleted. The example on the bottom is where foo doesn't allocate it on the heap, but it says, okay, I want to allocate it directly with myself. So it's a chunk of memory associated with foo that's reserved along with it. So if we're creating foo on the heap, then all it means is we will reserve a larger chunk of memory on the heap. And if we're allocating on the stack, exact same principle holds for that. So essentially, foo reserves a bigger chunk of memory compared to the one with a pointer to an additional item stored in the heap. So the bottom one is certainly faster, but is also less flexible, because we are explicitly saying it must be an instance of some class. That is what we are creating. The one on the top is more flexible, because I could create a class that extends foo, and if I wanted to, as opposed to having my sum class being linked in the heap, I could create a class that extends some class and have a more refined instance of it available in the heap and still be able to access it through this sort of, if you like, superclass pointer. So the top form, more flexible, bottom form, less flexible but faster. And in all of this, there is a trade-off between flexibility and performance. And generally, unless you need performance, in some cases you do, in some cases you don't, but unless you really need performance, it's generally better to go for flexibility or to favor that. Next up then is memory management, about how we or where data is stored in memory, and then some of the implications for that in terms of performance. A little bit of history, going back to early in the 90s. Your home computers The CPU, okay, it wasn't measured in gigahertz in terms of speed, it would be megahertz, but quite often, it ran, and it was at a point where the CPU was starting to run faster than actually the speed of the memory could run, or to be more precise, the speed of which affordable memory could run. So around then, CPU started being paired with caches, and a cache is basically generally a small amount of very fast memory. It's expensive memory, which is why you can't have a lot of it. And the idea here is that the fast processor would talk to the fast memory, and you'd have some other controlling mechanism that would try to keep the cache full of data that the processor is likely to need in the next short period. So this gets in then to saying that this cache, this area of particularly fast memory, and we still have it today, in fact we'll talk about it in the next slide, it's a bit more complex nowadays. We want to make sure that our program is written and structures its data in a way where we're more likely to find our data that is next needed by the processor in the cache and readily accessible. If we're looking at modern CPUs, we generally have several different levels of cache, so level 1, level 2, level 3. You also generally have a distinction between an instruction cache and a data cache. So you have one cache for holding the instructions which are likely to be executed next, and a separate cache for holding the data that's likely to be accessed next by way of terms of the instructions. Bit at the bottom gives you a flavor of just how much difference there can be between these different levels. So if it's stored in the register, the actual CPU itself, generally you can access it in that cycle. If you have to go out to level 1 cache, you may be talking about, say, 4 CPU cycles to get the data, where sort of waiting for that to come in. Level 2 cache, maybe 10 cycles. Level 3 cache, 75 cycles. Out to main memory, could be 200 cycles. So you can see that if you structure your application so that the data generally finds itself in the level 1 cache, then it's going to be an awful lot more quicker than if it has to go out to main memory. Who gets to determine? Okay, so the firmware in the computer, there'll be a bunch of hardware that predicts what data is likely needed, and it operates really in the principle of locality, that if you have accessed a piece of data at a certain location, then it assumes that you are likely then to want to access the data around that, the next one and the one after that. So generally that's the broad overview of how it selects what finds itself within the cache. If you have multi-core setup, you may have individual caches, you may have shared caches. Doesn't really matter. There's just variation across processors. So how does this actually affect us then as programmers? I'll show you an example here that maybe illustrates the general principle. But we want to think about how we access our data and also how we store our data in memory. And data that is accessed sequentially from one item to the next item to the next item, for example within a for loop, we want to, where possible, make sure that that data is co-located, is grouped together in memory, because then that will give us maximum opportunity to get into the cache and to get good performance. So over on the right hand side, actually look at the method first of all. We've got a method process lots of data, and it takes in a pointer to a data record and is working out the average value in that data. So we've got a line 4, we go over a number of records. Let's assume it's a lot of records, where we're adding up the average and then we're calculating at the end, or accumulating the total and then calculating the number of records then to determine the average. And we're saying likely lots of cache misses. Now, this assumes that we have structured it, the data as shown just above that. So struct data record. And inside our data record, we have 2 floats, one for average, one for standard deviation, and then we've got our data. And we're saying 100 items of data for each of our records. Now, if you think about how this is likely to be set out in memory, we will have one data record following another data record following another data record. Inside our process lots of data, this particular one, this is the one that calculates the average value. So imagine, let's say, an array of 10 data records. Each data record itself is 102 floats in size, so roughly about 408 bytes. So 408 bytes will be the first record, then 408 the next, 408 the next. We're accessing the average, so we will access the average of the first one. To get the average of the next record, we have to jump forward 408 odd bytes in memory, and that then gives us access to it. To access the one after that, we have to jump forward another 408 bytes in memory. And because we are jumping forward, we're taking fairly big steps. We're not sort of accessing the next value. This is going to cause issues to the caching algorithms because it will cache the data around it. It will cache those next 408 bytes. And because our level 1 cache is of a reasonably small size, same with level 2, level 3 bigger, main memory bigger again, we're likely to end up skipping over a lot of the information that's in level 1 cache, hitting level 2, hitting level 3, potentially hitting main memory, and that's going to slow it down. Over on the right hand side shows you how we might more efficiently structure our data. So in this case we have separated out, we've got our raw data and we have our data stats in a separate struct. And in this one here we have the average and standard deviation stored in the zone. So if we were to then change process lots of data to one that was, process lots of data but takes in the data stats, this is the thing that it works on. In this case here, we're accessing the average of the first one. We then have to skip 4 bytes, which is the standard deviation, and we get the average of the next one after that. So there we're only jumping forward and skipping 4 bytes at a time in terms of wasted information. So that means we're much more likely to get all of our data structs stats into the level 1 cache, and it'll be accessed much more quickly. So general principle holds there. How we access data depends on methods, depends on the ones we do frequently, but we want to try to make sure that something that is called frequently, that does a lot of work, that the data it is accessing is all stored in roughly the same chunk of memory next to each other. If we do that, if we accomplish that by way of how we arrange our data structures, that will give good cache alignment, that will give good performance. Temporary variables, we'll end then by talking a little bit about temporary variables, but this is also going to link into the next and indeed the final talk that we have on optimization for return value optimization, or RVO. Now, temporary variables, they're almost a necessary component of it. These are things that are generated by the compiler as a means of calculating or working out or doing whatever we want to do. They're temporary in the sense that they exist for a little period of time. So if I say one int plus another int, so there we have to add them together, we might get a temporary variable holding the result of that. At some point then we're going to discard, get rid of that temporary variable. Now, it could be primitive data, could be an object as being the temporary values. What we need to understand here is the conditions under which temporary variables are likely to be created. And we've got an introductory example here. So we've got a class called rational. It just represents a rational number, overloads the plus operator, but neither here nor there. We've got a default constructor, parameterized a couple of default values for numerator and denominator, and we've got our 2 private values. So fair enough. Underneath that, we have 3 ways of creating a rational instance. Line 1, we're saying rational R1, and we actually are calling the constructor directly. And in this case, there definitely never ever will be any temporary objects created. It will always give you R1 and it will be created directly. Now, the other 2 shown in lines 3 and lines 4, they might result in a temporary value being created. A good compiler won't do this, and any compiler we're using won't do it, but there's a possibility that actually you might get a temporary object being created. So in line 3, rational R2 is equal to rational 100. And now, potentially what we might do here is to create a temporary variable, an R value we can't refer to directly, holding rational 100. And then to use the copy assignment constructor to copy that across into R2. In line 3, similar process, we could see 100. We could then maybe think, okay, can we turn 100 into a rational instance? We can. We'll call the constructor will do that implicitly, gives us an R value. We'll then call the copy assignment constructor, and it copies across into R3. So potentially 3 and 4 could give you a temporary R value. It needs to be created and then deleted. It's unlikely though. How does these things come about? It really comes into to implicit conversion. So we can see the example here of rational R, and R is equal to 100. Because the order in which the compiler will do this, if you have the line 2, R is equal to 100, it's first going to check to see if R has an assignment overloaded operator which accepts an integer. So we can assign one R equal to another R. So I can say R1 is equal to R2, and we'll have that copy assignment constructor. I could also, there isn't in this case, but I could also overload my assignment operator to say that I can accept an int. I don't have to accept another instance of my class. I could accept whatever I want. So it checks first of all to see if there's an assignment, an overloaded assignment operator accepting an int. There isn't in this case. Failing that, it then checks to see if I have an int, can I construct a rational number from that? It can. There's a constructor that will do that. So it uses that then to create this temporary variable, and then the copy assignment constructor that is defined for the rational class gets to be called to copy it across. And you can see the potentially the 4 lines of code that get to be executed at the bottom for our rational number, constructing it, and then using the copy assignment constructor to copy it across, and then finally we need to delete the temporary variable. Little aside, C++ actually gives you, if you don't like the compiler implicitly calling your constructors, sort of looking at the list of constructors and you have and saying, oh, I'm going to call that because it sort of serves its implicit conversion needs, you can actually deny this particular ability. And C++ 11, you have what's known as the explicit keyword. And if you put explicit in front of any of your constructors, it's basically an indication to the compiler that, okay, I as the programmer, I can explicitly call this constructor, but you as the compiler, you are not allowed to implicitly use it. So it gives a way of sort of preventing unintended implicit conversion. That's quite a good idea. Now, nearly finished, and we want to really do a little bit of linkage here into the next talk, where we're going to look at a specific optimization known as the return value optimization. Now, temporary values. If we have a method that returns an object of a particular type, this is a good candidate for having an R value being created that we may not be able to get rid of, we may have to live with. So let's have a look at an example here of some string manipulation. So string S1's first, string S2's second, string S3. And line 5, which really should be line 4, we say S3 is equal to S1 plus S2. Now S1 plus S2, what happens first of all for this one is that we go to the string class and we see has the string class overloaded the plus operator so that we can add together 2 strings. And the built-in one actually does overload the plus operator, so you can concatenate 2 strings. So that's an available method. It calls that concatenation method, and that concatenation method returns a new string. So this is our temporary R value. We can't access it directly. It's a temporary value holding the concatenation of that string. We then say that, okay, S3 is equal to this temporary R value. and we go to S3, we say, okay, do you have a copy assignment constructor for a string? There is, use the default one, the one that's built in, and we'll then use that to copy the temporary R value across into S3. And having done that, the temporary value is sort of finished its usefulness. We then get rid of it. Now, why does this S3 is equal to S1 to S2? Why does it generate a temporary in the first place? The reason for that is that if we think back to when we were looking at our constructors and classes, and when we were defining the copy assignment constructor, so it is a method that S3 makes available, and it accepts as a argument, its parameter is another string. So we have to, if we're going to call this, be able to have something we can pass into S3 to say, here's a string for you to copy from. And because we have a need of passing in that string, we have to create one. This is the temporary variable, how it actually exists in that case. Now, there's one small caveat in this here, and this is an explicit optimization that comes in, and it's to a certain extent, you look at the definition of the copy assignment constructor, it's clear. You're going to call it in the object, it needs another string coming in, there has to be a temporary R value. Has to be, maybe not. If, and this is the key, if S3 is a brand new string and it hasn't yet been constructed, and this is the necessary condition, so S3 must not have been constructed at this point in time. If that is the case, then the compiler can do something a bit different. It still has to create the temporary variable, but instead of then going to S3 and constructing it using the copy assignment constructor, it can just say, okay, I'm going to ignore that, and this temporary variable, I'll use that as S3. So effectively, your temporary variable is S3 all along. And that's something known as the return value optimization. And we'll look at that in a bit more detail in the next talk. By way of summarizing this particular one, two different ones. Minimize memory management calls. So generally, if we're creating things, try to create them on the stack where possible. It does limit flexibility. Now, okay, little side. If you're using C#, you do actually have options here. C# also supports structs. Structs are value types, so they're created on can be created on the stack. Java doesn't support structs, as object-based. So anytime you create an object in Java, be it as part of another class, it is going to be stored on the heap. That can be more problematic, and either you use something like an object pool to avoid or to minimize those costs, or you untangle and you sort of reformulate the operations into using primitive data that can be stored in the stack. It's a little bit more difficult to have control over this, for example, in Java. C++, very straightforward, very easy. Second one, we should write cache-friendly code. We should think about our algorithms, think about how they access data, and try to make sure that we are arranging our data in memory so that our algorithms access it nearby, sort of stepping over from one piece of data to the next without doing large jumps through memory.